Hi everyone and welcome back. Hopefully you are feeling good about the work that we've done on fuels and obtaining energy from fossil fuels and biofuels. So looking at chemical potential energy, transformations using thermal energy, mechanical energy, and then into our turbines to generate electricity. Now we're going to be continuing our studies in energy, but looking at redox processes. And these are the processes where we use chemical reactions, redox reactions, in order to generate energy and then harness that energy for batteries. So we're going to be moving into looking at a lot of work on batteries, both rechargeable and otherwise. For galvanic cells as a source of energy, in terms of what VCAR wants us to be able to do, we need to be able to look at redox reactions with reference to electron transfer, reduction oxidation reactions, reducing and oxidizing agents, and the use of oxidation numbers. We covered all of this in year 11, so you can go back and look in detail at those videos from the year 11 videos if you wish. I will link those here. But we need to also start to extend on this. So we're going to be looking at balancing half equations for oxidation reactions, balanced ionic equations, including states for overall redox reactions. So you need to really work on these ideas of ionic equations, making sure that you are familiar with the rules of those. Then we will move applying these rules of chemistry into galvanic cells, energy transformations in terms of spontaneous exothermic reactions, and then the electrochemical series determining the voltage that will be given by a cell. But for this video, we're just going to review these ideas that we did in year 11, have a quick review of balancing half equations. Again, if you want to look at this in more detail, make sure to go back and check those older videos. So for this video, we're going to be reviewing the key terms of vocabulary associated with redox. We're going to look at the rules for determining oxidation numbers. Make sure to have these in your notes so you can be practicing, perhaps even annotate your data booklet that you're using with those rules on your electrochemical series so you have them close to hand while you're studying. Then we're going to practice applying those rules to determine the oxidation number of different elements and use those change in oxidation numbers to justify whether or not a redox reaction is occurring, as well as being able to identify both the oxidant and the reductant. So let's get started. Key definitions for this and the redox unit, it's critical that you can be able to identify the different parts of the vocabulary for this. I recommend using the Quizlet set to keep reviewing these terms so you get them fixed in your head. Defining a redox reaction, we're talking about the transfer of electrons from one chemical to another. So anytime we have transfer of electrons, say in the formation of an ionic substance from elements, or changing the charge on a metal, so going from neutral to a charged species, or in fact a combustion reaction, which is also a type of redox reaction as we'll see later, we are talking about a reduction and oxidation process. Oxidation, of course, is defined as the loss of electrons, reduction being the gain of electrons. These two processes cannot happen independently. It happens simultaneously. We can't have oxidation occur without reduction occurring at exactly the same time. So we have a mnemonic for remembering these, and that is the oil rig, standing for oxidation is loss, reduction is gain. Some people like Leo the lion says G, which is loss of electrons is oxidation and gain of electrons is reduction. Whichever works for you in terms of making it clear and easy to remember is the mnemonic you should use. So the oxidizing agent, also known as the oxidant, is the species that causes oxidation to occur. So because it is causing oxidation, okay, i.e. it is promoting something else to lose electrons, it will be reduced in the process because in order to cause oxidation in something else, it needs to be gaining those electrons. Which means that the reducing agent or the reductant, the thing that causes the reduction of something else, must be giving up electrons. So oxidation is loss of electrons. It will be losing electrons. So the reductant is always oxidized. When we talk about half equations, these are equations where we break up the main chemical equation into one half of the equation which depicts the reduction process and the other half of the equation that depicts the oxidation process. Half equations will show the electrons. So the reduction half equation will have the electrons on the left-hand side because the electrons will be a product, they're being put in, and the oxidation process will have the electrons on the right-hand side. So when we look at oxidation, we can define oxidation as a process where electrons are lost, therefore they are produced. So they will be a product in the chemical equation. Reduction is a process where electrons are gained. They are being consumed. They are a reactant in the chemical equation. So if electrons are to be lost, there has to be another atom present which can gain the electrons. So oxidation and reduction always occur spontaneously. In order for something to be given up, there needs to be something to be received. So it's just basically like if you're throwing a ball between two people. If you just throw something and there's no one there to catch it, nothing's really going to happen. So the electrons are being thrown from one atom to another, and obviously there will be a change in charge that is associated with this if it's a complete electron transfer, say in the production of an ionic compound. To that end, if you remember back to the prac that we did with magnesium oxide back last year, okay, where we took a piece of magnesium metal and it was reacted with oxygen in the air, and what was produced was magnesium oxide. This was one of the first introductions to stoichiometry that we did, and we worked out percentage composition. So what we have here is a neutral compound of magnesium, a neutral piece of magnesium that is reacting with a neutral molecule of oxygen to form an ionic compound. So in this case, we must have formed an Mg2+ ion and an O2- ion in order for that ionic compound to be balanced. So the magnesium is the reductant because it has given its electrons to the oxygen, which is reduced. And we can see that the magnesium has lost electrons, so it was oxidized. The oxygen has gained electrons going from neutral to -2, so it is now being reduced. It has gained electrons. Where it's obvious for ionic compounds, it becomes less obvious when we have combustion reactions where we're dealing with covalent molecules. The electron transfer in these processes is not complete, i.e. we don't form ions, so we can't use the change in charge to inform us whether a redox reaction has happened or not. So what we tend to do, because these electrons are being shared, we need another way of doing this. Traditionally, oxidation was considered to have happened if something increased its amount of oxygen. So if you have a look here, the carbon has picked up oxygen, so it has been oxidized. Okay, if something has been reduced, then we increase the amount of hydrogen or we reduce the amount of oxygen. Okay, these bonds, however, are polar, so we know the electrons aren't shared equally. So we use oxidation numbers to show us how the electrons are being moved about within the molecule. When we use oxidation numbers, it allows us to work out if a reaction is a redox reaction without relying on whether or not it's ionic and being able to look at more closely into the reaction. So we can use oxidation numbers to determine if a reaction is a redox reaction, i.e. if there is a change in oxidation number, then we know that a redox reaction has occurred. No change in oxidation number, no redox reaction. They are defined to enable reactions involving molecules as well as ions to be described as redox reactions. They have no physical meaning. They don't actually relate to the charge. They don't relate to the way that something behaves. They are a tool used by chemists to determine differences in redox reactions. okay? And we use rules, same rules all the time, applied consistently in order to determine the oxidation numbers. So in this case, using oxidation, it is important to remember that oxidation is associated with an increase of oxidation number. So before we saw that magnesium went from an oxidation number of 0 to an oxidation number of +2, and we said it had lost electrons, so it was being oxidized. And we can see here, 0 to +2, the oxidation number is going up, so oxidation has occurred. In terms of reduction, reduction is defined as occurring when there's a decrease in oxidation number. So if we look at the oxygen from our example before, it started at 0 and it went to -2. The oxidation number has gone down, so we have a corresponding reduction process occurring. These are the rules for oxidation numbers. You should make note of these. Let's go through them quickly. The oxidation number of each atom in a pure element is 0. So if it is a metal, a solid piece of metal, or liquid if it's mercury, oxygen gas, so O2, P4, S8, anything that is in its elemental form at room temperature, it is going to have a 0 oxidation number. Oxidation numbers in monoatomic ions, i.e. things just of that element, is equal to the charge on the ion. So a sodium ion will have +1, a sulfide anion will have -2, nitrogen nitride anion will have -3, and so forth. Where compounds contain oxygen, oxygen is considered to have a oxidation number of -2 unless it's bound to something that's more electronegative, i.e. fluorine, in which case it changes to positive because the fluorine will be negative, or in peroxides such as H2O2. This is an exception, and oxygen is -1 in this case. Compounds containing hydrogen, hydrogen is always +1 unless attached to something that is more electropositive than it. So metal hydrides, the hydrogen is -1. And we can see that in the name because the hydride, it ends in IDE, so it's telling us that the hydrogen is acting as an anion in this case. For a molecule, we use basic algebra in order to determine the overall sum of the oxidation numbers and work out the one that is known. So in this case for methane, we don't have a rule for carbon. Carbon can have a changeable oxidation number. So hydrogen is +1, so I've got 4 lots of +1 that I need to balance out, which means carbon must be -4 because it needs to sum to 0 overall because there is no charge on this molecule. For polyatomic ions, we always sum to the charge on the ion. So for PO4, we're going to be adding up to -3. Oxygen is always -2 in a molecule, so we're going to have -8. To get to -3, I need to add 5, so we're going to get +5 for the oxidation number on phosphorus. For a compound, the most electronegative element is assigned to the negative oxidation number. So in this case, where we have SF6, fluorine being our most electronegative element will be negative. So this means that fluorine would be 6 lots of -1. So -6, I need to add 6 to get to 0. So the sulfur will have an oxidation number of +6. Once we know how to calculate oxidation numbers, we can apply them to determine if a redox reaction is happening. So if we look at this example looking at potassium dichromate, we can see here, if we're going to calculate the oxidation number of chromium, we have potassium. Each potassium is +1. Each oxygen is -2, so I have -14 being contributed by the oxygen, +2 from the potassium, so -12 overall, which means 2 chromiums need to add up to +12. The oxidation number on chromium is going to be plus 6. And if we follow the working through, that is exactly what we see. We get 2x is equal to plus 12, so the oxidation number on chromium is plus 6. So what I want you to do in your notebook is to determine the oxidation number of each element in the following. Have a go, pause the video, and then come back and check to see if your oxidation numbers were assigned correctly. Okay, so hopefully you came up with the answers that I have done here. The first few are fairly straightforward using our rules, and then once we get to the bottom two, there's a couple of tricks. This is aluminium hydride, so our hydrogen is going to be plus 1. Sorry, our hydrogen is going to be minus 1. Okay, for each hydrogen, making the aluminium plus 3. And then the S2O3, there was just a typo here, this should be minus 2, which makes our sulfur plus 2 because our oxygen is minus 2. Hopefully you have gotten a grip on that. Practice is the key, making sure that you can apply those rules quite comfortably. So as I said before, if the oxidation number increases, then the oxidation process has occurred. If reduction occurs, then the oxidation number will decrease because electrons has been gained. So if we determine whether or not an oxidation reaction has been occurred, we need to find a situation where the oxidation number has increased and oxidation number has decreased. We can see here that the carbon goes from an oxidation number of 0 to plus 4. So carbon goes from 0 to plus 4. The oxidation number, okay, has increased, therefore it is being oxidized. And then for the oxygen, O2 goes from 0 to minus 2, so the oxidation number has decreased, so it has been reduced. The substance that is reduced is the oxidant, and the substance that is oxidized is the reductant. And as you can see, this is a combustion reaction. Combustion is a redox process. Okay, so have a go at this one. Use the oxidation numbers to determine which reactant has been oxidized and which has been reduced, and come back and check your answer. So if we apply oxidation numbers to each of these, we can see that the sulfur is plus 4 because it balances out the minus 4 from 2 lots of oxygen. Nitrogen, again, also plus 4, so they start off at the same oxidation number. After the reaction occurs, sulfur is plus 6. We now have 3 lots of minus 2, so to balance it out, sulfur will be plus 6. And then with the nitrogen and the oxygen, minus 2 for the one oxygen, so nitrogen is plus 2. Nitrogen has gone from plus 4 to plus 2, so it has been reduced, undergoing a reduction process. And sulfur has gone from plus 4 to plus 6, the increase in oxidation number showing that it has been oxidized.
Terminology for redox can be quite confusing. With all the terms oxidation, reduction, oxidizing agent, reducing agents, they all sound very similar. It is important that you practice this terminology so that you can use it in the correct way in the right situation. The reactant that gains electrons is reduced, remembering reduction is gain, from our rig, from our oil rig, and it's called the oxidizing agent. It is the thing that facilitates oxidation in another species. The reactant that loses electrons is oxidized and is called the reducing agent or reductor because it causes reduction in the thing of which it is giving its electrons to. So in this case, and it is important when we're identifying reducing agents and oxidizing agents that we use the entire species. So in this case, because the iron in Fe2O3 goes from plus 3 to Fe0 on the right-hand side, Fe2O3 solid is the oxidizing agent. Carbon goes from carbon solid to carbon monoxide gas from 0 to plus 2. Carbon solid is the reducing agent. Okay, so we need to make sure that we take the state and the full formula of the compound that contains the atom that is being oxidized or reduced when we identify the oxidation agent or the reducing agent. So if we look at this reaction again, we can see that the reducing agent brings about the reduction of Fe +2 to 0 and is oxidized from 0 to +2. The oxidizing agent Fe2O3 brings about the oxidation of carbon by itself being reduced to Fe, so it gains electrons from the carbon. When we look at these and we can match up the thing that is being oxidized and the thing is being reduced, what we're doing is creating what we call a conjugate redox pair. So in this case, the zinc, which goes from 0 to Zn2+, is the one pair, and then Ag plus going from +1 to Ag solid is the other conjugate redox pair. And these are what we look for when we go to pull out the half equations for the reduction or the oxidation process. I want you to have a go at these VCAR questions. I'm going to end the video here because you've got the questions that go along with them. Our next video will be a quick review of redox half equations and moving on how to balance more complex redox equations, which is some new stuff that we haven't covered before. Good luck with all your study. Make sure you have a go at these questions to consolidate the information, and I'll see you in class.